Okay, so today we are doing the Lagrange error-bound review. So first problem I have up here, let f be a function that has derivatives of all orders for all real numbers x. Assume that f of 5 and all its derivatives are shown here, and then for all x in the interval 5 to 5.2. So first find a third-degree Taylor polynomial about x equals 5 for f of x. So it gives us all of the values of the derivatives at, the function at f equals 5, then the derivative at 5, the second derivative at f at 5, etc. So we just plug that into our formula, which is the nth derivative of f at x over n factorial. And since this is a Taylor polynomial centered at x equals 5, this would be x minus a normally to the nth power, but since we know we're at f5, this should be an a, sorry. And so this would be 5, and this would be 5. So we can just plug everything in. So first we have 6 over 0 factorial times x minus 5 to the 0, which is obviously just 1, so I just write a 6. Then we're add 8 over 1 factorial, or just 8 times x minus 5 to the first power plus 30 over 2 factorial times x minus 5 squared, and plus 48 over 3 factorial times x minus 5 cubed. And then these can be rewritten. 30 over 2 factorial is also just 15. And then 3 factorial is 6, so this is just 8. And then this is the same. So it's part A. Now part B, we are to use our answer from part A to estimate the value of f of 5.2 was the maximum possible error making this estimate. So this is the Lagrange error bound. First, we'll just estimate the value of 5.2. So we're just plugging in 5.2 for x. So that's just 6 plus 8 times 5.2 minus 5, which is just 0.2. So, like so. And that equals approximately 8.264. So you can just use a calculator for that. And now we have to estimate the maximum possible error in this estimate. So that would be the Lagrange error bound, which means we have to take the n plus 1th derivative at a, so at 5 in this case, and then multiply that by x minus a, or 5.2 minus 5 to the n plus 1th power over n plus 1 factorial. So since since n is 3, right? Because we see this goes to the 3rd power, we'll just do the fourth derivative. So it gives us that f of 4. Oh, this is not of 5. This is of z. I always forget that. Which means from on the interval a to x, this is the point z is where the nth plus 1th derivative has the maximum value. So just for example, if this is the graph of the n plus 1th derivative, and then this is A, this is X, or something like that, then this would be Z, because it's the maximum value. And usually Z will be at one of the endpoints for these problems. Or in this case, it just tells us that the fourth derivative is always going to be less than or equal to 75. So we'll use that as our maximum value. Then multiply that by 0.2 to the fourth power over 4 factorial, which gives us approximately 0.005. So now look at part C, which is to find an interval from A to B such that A is less than or equal to f of 5.2 is less than or equal to B, which is pretty much just taking our estimate of f of 5.2, which we found to be 8.264, and then subtracting our error for A, and then adding it for B. Because, right, this is our estimate. This is our estimate. And then this is our error. So by adding it, or this is our max error, right? So by adding the max error, we'll know that the value must be less than A, and then, or it must be greater than A by subtracting the max value, and then by adding the max error, we know that it must be less than B. So this gives us 8.259 is less than or equal to f of 5.2, which is less than or equal to 8.264. There we go. And then I don't have it written, but part D just asks, could f of 5.2 equal 8.254? And 8.254 we can see is less than this, which means that no, it could not fall in the interval. Or it cannot equal that because it does not fall in the interval. So that's number 3. Now let me pull up number 4. Oops. There we go. So we're finding the first 4 non-zero terms of the power series for f of x equals sine x, centered at x equals 3 pi over 4. So normally we'd have this memorized, right? The Maclaurin series of sine of x, but since this is centered at x equals 3 pi over 4, we can't use the formula. So instead, let's just write out the first 4 terms of the power series, or we'll just write out the first 4 derivatives, and then the derivatives at sine of 3 pi over 4. So f of x equals sine of x. Now the first derivative of that is cosine x. And the second derivative, negative sine x. The third derivative is negative cosine x. Now we'll say x equals 3 pi over 4. So sine of 3 pi over 4 is rad 2 over 2. Then cosine of 3 pi over 4 is negative rad 2 over 2. Then negative sine is negative rad 2 over 2. And then negative cosine rad 2 over 2. So plug that into our Taylor series thing, and we get rad 2 over 2 minus rad 2 over 2 times x minus 3 pi over 4 minus rad 2 over 2 over 4, or no, over 2 factorial, which you can simplify if you want, but I'm just going to leave it like this. And then this is squared, and then plus rad 2 over 2 over 3 factorial. Cubed, x minus 3 pi over 4 quantity cube. So that was number 4, not too tricky. Moving on to number 5. We have, oh, paste it up here. Here we go. We are finding the first 4 non-zero terms in the general term for the Lagrange series of each of these. So since we're using the Lagrange series, we see the cosine of x cubed. So first we'll write down the first 4 non-zero terms of just cosine x, which is what is it? 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. And now that's cosine x. Oh, let me move this. There. So approximately equals that. Now when we want to look at cosine of x cubed, we can just plug in x cubed everywhere there's an x. So that becomes 1 minus x cubed squared, or x to the 6th over 2 factorial, plus x cubed to the 4th, or x to the 12th, over 4 factorial, and then minus x cubed to the 6th, or x to the 18th, over 6 factorial. And now we're multiplying by x. So we just multiply by x minus x to the 7th over 2 factorial, plus x to the 13th, over 4 factorial, minus x to the 19th over 6 factorial. And so we can see the general term is x to the 6n plus 1. Or wait, sorry, it's alternating. So negative 1 to the n times x to the 6n plus 1, because we start at n equals 0, right? Over 2n factorial. And so if we just look at the general terms, we can see, so the general term of cosine x is negative 1 to the n, x to the 2n over 2n factorial. And so when we introduce the x cubed, we can also just plug in the x cubed right here, which means x cubed to the 2n is just x to the 6n. So that becomes this, right? And then once we multiply this by x, it's just adding the plus 1 right here, because that's the exponent rule, and that's how we can just look at the general term and also solve for that. So now we'll do 1 over 1 plus x squared. This one is pretty easy because we know that the power series is just 1 over 1 minus x, which equals this, right? So this is just replaced with an x squared, and it's a negative x squared. So 1 over 1 minus negative x squared. We can just replace that negative x squared to the n, which is negative 1 to the n, x to the 2n. And then we can just use this to construct our first four non-zero terms. And so we get 1 minus x squared plus x to the fourth minus x to the sixth. So we can see in part A, I looked at the first four terms and then I constructed the general term, and then in part B I constructed the general term and then I used that to create the first four terms. So either way works. It's just personal preference of which one you do. So that was number 5. Now number 6. Is finding the radius and interval of convergence for these two series. I don't know why my thing says control. Huh? Hold on. Why does it say control? Oh, don't do that. Oops. No, how do... Oh. It still says control. Oh, there we go. Sorry about that. So whenever we're finding the radius and interval of convergence, we are using the ratio test. So we will take the limit as n approaches infinity of this whole thing, but to the n plus 1, or not to, like using n plus 1 instead of n plus 1 over n plus 1 squared. And then we are dividing this by we're dividing this by just this. So this would go on the bottom. But just to make the math appear a little bit easier, I'll just multiply it by the reciprocal. So we have 3 to the n over n squared, or times n squared, over negative 1 to the n times x minus 2, quantity to the nth power. This is all absolute value. And so I use red. The 3n cancels with the 3n, and we're left with 3. And then this cancels with that, and we're just left with negative 1. And this cancels with this, and we're left with x minus 2. So this becomes limit as n approaches infinity with the absolute value of negative, that's the negative 1, negative x minus 2 times, I guess I'll do n squared over here, over 3 times n plus 1 squared. And so since we're taking the limit as n approaches infinity, and these are the same degree, these will just cancel out to 1. And so we're left with the absolute value of x, x minus 2 over 3. And this must be less than 1. So if we, that's a bad 3. If we convert this to take out the absolute values, we see that we get this, which becomes, oh, what's wrong with the 3s? There we go. Or becomes negative 1 is less than x is less than 5. But we have to test, or so the radius of a convergence is 3, because the whole thing, right, x is between -1 and 5, which is 6, sort of a 6-unit range, and then divide that by 2, so we get the radius is 3. And then the interval of convergence we have, but we have to test the endpoints now to see if x can be at the endpoints. So if we plug in -1 to start, we get this sum, -1 minus 2 to the n over 3 to the n times n squared. And so this becomes -3 to the n. I guess I'll do that right here. Over 3 to the n squared. And so -3 just equals, we'll separate out the negative, so we'll get -1 to the n times -1 to the n times 3 to the n over 3 to the n squared. So these cancel out. Then 3 to the n, or -1 to the n times -1 to the n equals -1 to the 2n, which means that since we're multiplying by 2, the power will always be even, which means that this is just 1, so these cancel out. And so we're left with the sum, or I forgot the sum symbol here, of 1 over n squared from n equals 0 to infinity. And so this is just a p-series where p equals 2, so that converges, which means that -1, x can equal -1, so we will say -1 is less than or equal to x. And now to test 5, I guess I'll just do it below. So we're just plugging 5 now. And so this is just 5 minus 2 is 3, so the 3 thens cancel out, and we're left with -1 to the n over n squared. And this is just an alternating series. And the limit of 1 over n squared as n approaches infinity is 0, which means that this also converges. So 5 is also in our range. So this is our final interval of convergence, or it can be written like this as well. And then our radius, like I said, is 3. So now we will do the next one, which is 2n factorial times x minus 5 quantity to the nth power. And I guess I'll talk about that later. So first, we'll just do the ratio test. How do I do this? Let's see. Nope, that's not what I wanted. Yeah, we'll just remember what it equals. So, oops. We'll take the limit as n approaches infinity of, the top will be to the n plus 1's power, so 2 times n plus 1 factorial is just 2n plus 2 factorial, so I'll just write it like that, times x minus 5 to the nth plus 1 to the n plus 1th power over this. And it's the absolute value. So now this simplifies. Use red again. And we get that the 2n plus 2 factorial is just, I'll write it off to the side, 2n plus 2 times 2n plus 1 times 2n, right, etc. And then this is just 2n dot dot dot. So these cancel out, and we're left with just this part. So this equals the limit as n approaches infinity of 2n plus 2 times 2n plus 1 times x minus 5. And so obviously we can see that these are going to infinity, right? So the only way that this will converge is if x equals 5, because then this will be 0 and the whole thing will equal 0. Then this will be 0 and the whole thing equals 0. So it only converges at x equals 5, which means the radius of convergence is 0. And if we look back at the original problem, we can see that just intuitively looking at it, since there is no fraction, this will just keep getting larger without bound, unless, right, if we look at this, x equals 5, because then the whole thing is 0. And we're just adding zeros, which obviously converges. So that's sort of a more intuitive way to look at it, but this is the actual math that shows it. Okay, so now we will move on to number 7. Let me just grab it really quick. Use the Lagrange series for cosine of x to find the limit as x approaches 0 of 1 minus cosine of x over x. So what we do whenever we see this kind of problem, we're taking the limit and it's asking us for either the Lagrange or Taylor series, is we can just substitute, in this case it's the Lagrange series, in for cosine x, right? Because cosine x equals this series, negative 1 to the n, x to the 2n over 2n factorial. So we can just sub in, let's just look at like the first 3 terms or so. Hold on really quick. So the first 3 terms, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, etc., etc. And then we'll plug this into our limit. And we can see, well, this 1 and this 1 cancel out. And so we'll distribute the negative, and we'll be left with the limit as x approaches 0 of positive x squared over 2 factorial minus x to the 4th over 4 factorial, etc., over x. And I guess I could just do this like 1 over x. So then these cancel out, right? The x squared and the x to the 4th and the x. And we're left with the limit as x approaches 0 of x over 2 factorial minus x cubed over 4 factorial. And if we want the general term, it is, see, the first one is like this, x to the n plus 1 over 2n, 2n plus 2 factorial, I believe. Right, let me just check that. Yeah. If we're starting at n equals 0, which we could just start at n equals 1, but we'll start at n equals 0. And so we can see that as x approaches 0, then just these, the x is always in the numerator, so these all equal 0. And so the limit equals 0. So that's how we do number 7. It looks tricky at first, but once you do one of these types of problems, you can do pretty much all of them. So yeah. Now we'll look at number 8. So now number 8 asks or gives us the Taylor series about x equals 3 for a certain function f, which converges to f of x for all x in the interval of convergence. And then the nth derivative of f at x equals 3 is given by this formula. So first we are to write the fourth degree Taylor polynomial for f about x equals 3. So you could just plug in, n equals 0, and then, or I guess it gives us n equals 0 is just 1/3. But you could plug in like n equals 1, and n equals 2, n equals 3, all the way to n equals 4. And you could get the derivatives that way, but one thing that makes this slightly easier, or just one thing that makes the work slightly easier, is I noticed that there's an n factorial in the numerator, and we know in the Taylor series there's an n factorial in the denominator. So right, it looks like f the nth derivative of n, this time at 3, over n factorial times x minus 3 over to the nth power. So if we replace this with this whole thing, we see that we do this. Times 1 over n factorial. And so these just cancel out. And then x minus 3 to the n. So the first term is given 1/3. Then let's plug in n equals 1. So that means -1 to the first power is -1. So this will be a minus. This will be negative. And then 5 to the n, or 5 to the 1, is just 5 times n plus 3 is 4. So that's 20. And then x minus 3 to the first power. And then the next one is n equals 2. So -1 squared is +1. Then 25 times 5 is 125. So we have that. And then now we'll subtract, because this is an alternating series. 5 cubed is 125 times 6, which is 750. And then lastly, we have a positive 1 over 5 to the fourth power times 7, which if you plug into a calculator is 4,375. X minus 3 quantity to the fourth power. So that is our fourth degree Taylor polynomial about x equals 3 for the function f. And now we're finding the radius of convergence for that, which, like we did in, what problem was that? Like we did in problem 6, we just used the ratio test. So finding the limit as n approaches infinity of the absolute value of -1 to the n. I'm substituting in the formula we're given because that's what the nth derivative of n is, of f is at 3. So we get this times 1 over n factorial times 3 to the n. And again, these cancel out. Or wait, no. My bad. Let's just do what we just did. So we'll rewrite this n plus 3 times x minus 3 to the n. So we cancel out the n factorials. Now, I guess we'll write this in the numerators because it makes more sense when we're doing the ratio test. Now we'll do the limit, and then we have to add 1, right, to n. N plus 1 plus 3 is just n plus 4, so I'm just going to write that. And then multiplying this by the reciprocal of what we just had. So 5 of it to the n times n plus 3 over -1 to the n x minus 3 to the n. And now we will simplify. So that, and that. It's negative again, but we're taking the absolute value, so really that's not necessary. But I'll just write it there. That's the leftover -1 that we have. And then we have x minus 3. Whoops. Times, or divided by 5. And then we have the n plus 3 over n plus 4. And so, whoops. And so since we're taking the limit as n approaches infinity, these just cancel out. And we are left with the absolute value of x minus 3 over 5 must be less than 1. Oh, and we're just finding the radius of convergence. So the radius is 5 because we can look at the denominator. And that's 5. So the radius is 5. But if you want to see the math, is just, right, we're multiplying first by 5. So or not less than equal to. Less than. And then at 3. So radius is still 5. And then normally we would need to plug in the endpoints if we wanted to find the interval, but since this only asks for the radius of convergence, we don't have to do that. So now part C is we are showing that the third degree Taylor polynomial approximates f of 4 with an error less than 1 over 4,000. So we actually found the fourth degree Taylor polynomial. But now we're just looking at the third degree. So this is again a Lagrange error bound problem. So we'll just take the n plus 1th derivative. Whoops. Why does that keep happening? Oh, there we go. We'll just take the n plus 1th derivative at x equals or at 4. Or no, this is at z, which is between f of f, or between 3 and 4. But since we're only given 4, or we're only given what happens at 3, I think we have to take it at 3. And then 4 minus 3 to the 4th. Whoops, this is to the 4th over 4 factorial. Oh, wait. Yeah. And then this, since we have the formula for this part, right, it equals -1 to the 4th times 4 factorial, whoops, over 5 to the 4th, 4 plus 3, or 7, and then times, this is just 1 over 4 factorial, so this cancels out. And we're left with 1 over 5 to the 4th times 7, or this, which is less than 1 over 4,000. All right, that's part C. Now, moving on to number 9. So let me just grab it really quick. There we go. Let f be a function that has derivatives of all orders on the interval -1 to 1, and we are given a bunch of values. So first we want to find the third degree Taylor polynomial that x equals 0 for the function f. So this is number 9. Okay, this is super similar to, which one was it that we did earlier? 3. Oh yeah, this is super similar to number 3. So we'll basically just do the same thing. And we'll write 1 plus 1/2 over 1 factorial, or just 1 half of, yeah, so this is about x equals 0. So this is also just the Maclaurin polynomial. So x minus 1/4 over 2 factorial, or 1/8 x squared, and plus 3/8 over 3 factorial, which is 3 over 8 times 6, or 1 over 8 times 2. So 1/16 x cubed. And that's the third degree. Now we're estimating the value of f of 0.5. So pretty easy, just plug in 0.5. And then if we calculate that out, we end up with 1.227 approximately. And then part C of this is the maximum possible error. I guess I'll just grab that. So this is just a Lagrange error bound, and we can see in the original problem that the absolute value of the fourth derivative of x is less than or equal to 6, so 6 is our maximum. So use 6 times 0.5 to the 4th, because this is just 0.5 minus 0, because that's where the polynomial is centered, over 4 factorial. And we're using 4 because we went to n equals 3 in part B, so now we'll go n plus 1, which is 4. And then when we calculate this out, we get 0.015625. So that is number 9. So now we'll look at number 11, which I'll just get really quick. So f of x equal the sum from n equals 0 to infinity of x to the nth power over 2 to the nth power for all x for which the series converges. So first we're trying to find the interval of convergence, which is again just the ratio test of the x to the n plus 1 over 2 to the n plus 1 times reciprocal to the n over x to the n. And so you could do a lot of canceling here. Basically just left with a limit, as n approaches infinity of x over 2. So that means x over 2, or the absolute value of that, must be less than 1, or x must be between -2 and 2. And so now we'll test the endpoints, starting with x equals -2. So if we plug that in, we actually get -1 to the n over times, -1 to the n times 2 to the n over 2 to the n, which cancels out. And this actually is just multiplying, or is just adding -1 and 1. And so I guess we're starting at 1. So this is just 1 minus 1 plus 1 minus 1 plus 1. So even though it doesn't actually get bigger, the series doesn't ever converge to one value. It just alternates between two values. So this is still divergent, which means that -2 is not in the bound. And so now we'll test 2, and we get 2 to the n over 2 to the n, or just 1, which is just adding 1 infinite times, which is obviously divergent. So this is our final answer. Now moving on to part B, we're using the first 3 terms to approximate f of -1/2. So now we'll just plug in, well, I guess we'll write it out first. It's easier. So x to the 0 over 2 to the 0 is just 1, plus x over 2 plus x squared over 4. And then plugging in 1/2, or -1/2, we get 1 plus -1/2 over 2 plus -1/2 squared over 4. And this equals 0.8125. So that's our approximation. And now we're estimating the error of this approximation. And so you can do an alternating series, because if you notice, whenever x is an odd power, like I'll show right here, x is odd, and x is odd, right? So this is negative, but then whenever x is an even power, this becomes positive. So this is an alternating series, and you can use alternating series error to get, here, I guess I'll just show it, to get -1/2 half cubed over 8, which is just, and it's the absolute value because it's error, right? Which is just 1 over 64. But you can also use Lagrange in this case, which is a bit trickier, but you don't have to realize that this is an alternating series. So for Lagrange, we need to know a formula for the for f of n, or the nth derivative of f. And so sorry, I got distracted. And so what we can do is, I guess this is at what? This is a Lagrange series. So what we can do is say that this equals the series formula which we're given. And so we can cancel this with this, and we'll multiply by n factorial on both sides, and we're left with the nth derivative of f at 0 equals n factorial over 2 to the n, which means, since we're looking at what, 3, n equals 3 now, because we went up to n equals 2, if we plug in that, we get 3 factorial, or 6 over 2 cubed, or 8, so 6/8, or 3/4. And then we'll plug that in, 3/4 times -1/2 minus 0 cubed. Let me, oh, wait, there. Over 3 factorial. And this actually also equals 1 over 64. They won't always do that, but in this case, they happen to equal the same thing. So that's C. Now, we'll move on to number 15, which is this. It's a multiple choice. The next 4 are all multiple choice. So we are supposing that f is approximated with a 4th degree to a polynomial about x equals 1. And if the maximum value of the 5th derivative between x equals 1 and x equals 3 is 0.01, then the maximum error incurred incurred using this approximation to compute f of 3 is one of the following. So this is just the Lagrange problem. It gives us the maximum derivative value, which is 0.01. So we're just multiplying 0.01 times x minus a. So it's centered at x, so 3 minus 1 to the, what is this, 5th power, over 5 factorial. And this equals, if you plug in to a calculator, 0.0026667, so E. Now for 16, what are all the values of x for which the series given converges? This is just a ratio test. So we've done this several times on this review already, so I'll just speed through it. And then, and I guess you can cancel it like that. x over n plus 1, which is always just going to be 0, which means it's absolutely convergent, so all real x work. Now, number 17. Right here. The coefficient of x to the 6th power in the Taylor series expansion about x equals 0 for f of x equals sine of x squared is one of the following. So since it's the Taylor series about x equals 0, it's just the Lagrange series, which is something we have memorized, or we should have memorized. I would highly recommend memorizing it because it makes things so much easier. But basically, sine of x is this x to the 2n plus 1 over 2n plus 1 factorial. And so if we replace x squared, or x with x squared, we get just this, right? So we're plugging in x squared, so x squared to the 2n plus 1, which if we're putting a power to another power, we could just multiply them. So x to the 4n plus 2 over 2n plus 1 factorial. And so we're finding the coefficient of x equals 6, which means 4n plus 2 equals 6, or n equals 2. So we'll just plug in n equals 2. Negative 1 squared is positive 1, so then that's just x equals x to the 6 on top over 2 times 2. 4 plus 1 is 5, so 5 factorial. No, what am I saying? That didn't sound right. Okay, n equals 1. So now this is negative, and then the bottom is a 3 factorial. So the coefficient is just negative 1 over 3 factorial. And that is negative 1/6. So that's A. And now finally, number 18, the max error incurred by approximating the sum of the following series by the sum of the first 6 terms is blank. So this is an alternating series, right? Because it starts positive, then goes negative, then goes positive. So the first 6 terms, this is actually only the first 5 terms. So the 6th term is actually, 5 over 6 factorial. And so for alternating series, we just look at the next term, and the error must be less than that, because this is a nice visual. If we have a number line, and so in this case, we're starting at 1. So let's just say this is 1, and this is 0. And so first we subtract 1 over 2 factorial, which is just 1/2. So we're going back, use red, to 1/2, which is right here. And then we're adding 2 over 3 factorial, which is 2 over 6, or 1/3. So we go back, but not quite as far. And then we subtract 3 over 4 factorial, which is again even smaller. And so we see how this kind of, it goes back and forth, but it eventually reaches just a point, or it reaches a value. And so we can see that the next term is always going to be smaller, or the terms after a certain term are always going to be smaller than that term, which means the max error will just be the next term in the series. Hopefully that made sense. So we can just look at 6 over 7 factorial and get 0.00119 which is A. And so, yeah, that is the whole review that was assigned. Good luck on the test, and hopefully this helped.